So we're on for that trip then?
Yeah.
Okay.
I already have the ticket. I already bought the train ticket.
Oh, okay. Oh,
Yeah, the ticket thing is the train ticket. I already got it. So.
okay. Don't send anyone around to rough me up. I will pay.
Yeah. So.
Okay. So let me just remind you some of the recent topics that we covered, because I'm going to need to refer to them today. So first of all, recall the area formula. And that is, you've got a Lipschitz mapping, and where M and A is contained in Rn. And remember, this the area formula is only valid when M is bigger than or equal to N. So you're mapping into a higher dimensional space. We start in, and this is Lipschitz. Then the formula was that the integral over Rm of the counting measure, so you count the number of points in the pre-image. dLm, that's the same as integrating the Jacobian factor. That's the area magnification factor, JFX dx. And remember, JF x is the square root of the determinant of the n by n matrix DIFX dotted with DJFX. So that was one of the major things. We had to struggle a bit to give the proof of that, but we eventually got through that. And then the other thing that we talked about was submanifolds. So you've got an n-dimensional embedded CQ submanifolds. We talked about those, how you can represent them locally in terms of local coordinate representations. Submanifold of some Euclidean space, let's say Rn plus k. And there we talked about the taking directional derivatives of Lipschitz functions that are just defined on M. So then we had F Lipschitz map into any dimensional Euclidean space. It doesn't matter. It could be real valued, or it might be mapping into some other Euclidean space. That doesn't matter. And this is Lipschitz. And we proved that you could take directional derivatives for Hn almost every x. You get lots of nice facts. You get that the directional derivative dtf exists. The directional derivative in the direction tor for every tor in the tangent space of x, and it's linear in tor. So that enables you to define the induced linear map. So then it follows that you can just take the induced linear map is defined to be that directional derivative, same as it is in Rn, same procedure that you use in Rn, except that now we're working on the manifold, and now tor are vectors in the tangent space. That was that, and then we also wanted to mention something else. Yes, or maybe that's better just to call this. So those were the two things I particularly wanted to mention. And let's call this star, because I'm going to refer to it in just a minute. So that was a summary of where we got to so far. And let's go a little bit further now. the first thing is that I claim that there's an area formula that looks just like this one that's valid when you're working on a manifold. Notice this one was for when we were working in Rn. I claim that there's this almost identical formula that works on a manifold. So first thing is claim there is an area formula for maps F, M. Now remember, M is dimension n, so it's the same thing. You've got to be mapping into a higher dimensional Euclidean space. So this has got to still be Lipschitz as usual. And this is mapping into Rm again as usual, but a usual condition that M has to be bigger than or equal to n. And the formula actually is identical to this. It's the same formula. Integral over Rm of H0, that's counting the number of points, A intersect f to the minus 1 y, dlm, integration with respect to the y variable, of course, here. This is dlmy. And what's that? Sorry, this is
about
this one. Yes, sorry. This is dHn. Sorry. dHnx. Yeah. And right. So this is dH. Oh, the way we've written it. Yeah, that's right. dHn. Did I do that right? Yeah. Okay. So. Yeah, but now I want to, that was general. There was no restriction on Q here, but now I'm using a different symbol because there is this restriction. Yeah, m bigger than or equal to n. And H0 dlmy, so the left-hand side is the same. And it's the integral now over m of jf. Now I've got to say what this means because we're no longer in the Euclidean space. So it's not quite the same, but I just got to say what this thing is. Oh, sorry, this is M, this is A, and this is valid for, this is dHn again, and this is valid for A contained in M. And I have to say what this is now. Well, JFX is exactly the same thing, except that instead of the standard basis vectors, these are partial derivatives with respect to the coordinate directions in Rn. Instead of that, you take the directional derivatives with respect to an orthonormal basis of the tangent space. But otherwise, it's exactly the same quantity. So in other words, you take square root det dTor, directional derivative. Remember, directional derivatives exist almost everywhere by this. dTor q, let's call it dTor I of f at x dotted with dTor j f at x. And here, tor 1 up to tor n is an orthonormal basis of the tangent space. So notice this makes sense almost everywhere by star, right? These two derivatives all exist. So you get the same thing. I don't think I'll give the proof of that. You don't have, of course, you don't have to go through the whole gruesome procedure that we use to prove it in Rn. This follows direct. So it's actually an exercise. Prove this by using the, by using the formula from Rn, using this formula, by using 1, that's the formula for Rn, applied to the composite of f with local coordinate representation. This is a local coordinate representation. So give that a try for yourself. If you get stuck, take a look in the text. You'll see the argument is just a few lines. Yes? which equation are we talking about now? Yes?
You're right.
Oh, I'm sorry. Sorry. This is, we're mapping into, this is DH. I'm sorry. Yeah, a little punchy today. Right. These are all integration with respect to HN. Likewise here, not LM, HN. Thanks, Joe. So notice the formula look identical though. It's just the only thing that changes is that in this one you have to use an orthonormal basis for the tangent space, whereas this one you're just using the ordinary standard basis for Rn. Okay, so that's, I'll leave that one as an exercise for you because I'm getting a bit short of time and it's not too difficult. As I said, if you do get stuck, just take a peek at the text. You'll see that it's explained there. Now there's one other thing I want to mention, and that is in this, when we're talking about submanifolds, I want to mention the Cartesian product of two submanifolds, or product manifolds. That's rather important. In fact, we'll make use of it a bit later when we talk about currents. So suppose that M1 and M2, so suppose that Mj, for j equals 1, 2, Nj dimensional, so that's N1 dimensional for, so the Nj dimensional embedded CQ submanifolds. CQ submanifolds of N plus K, Nj plus Kj. So we've got two objects like that object at the top of the board there. One of them's got dimension N1 and it's in Rn1 plus K1, and the other one's dimension N2, it's in Rn plus N2 plus K2, right? So just two such objects. And then take local coordinate representations for these. So let Cj from Vj into Wj be local coordinate representations. For these. So that means that in particular Cj of Vj is equal to Mj intersect Wj. And consider the product of V1 Cartesian product with V2. Now remember, V1 is by definition of local coordinate representation. This would be in Rn1, wouldn't it? Nj. So this would be contained in Rn, where n is equal to n1 times n2. N1 plus n2. So this is n is equal to n1 plus n2. So this is the Cartesian product of Rn1 cross Rn2. So let's look at the Cartesian product. I want to cook up a local coordinate representation for M1 cross M2. I claim that M1 cross N2 is, again, a submanifold in this sense. I guess everyone believes that, but we want to check how that works out as far as local coordinate representations are concerned. So I'm going to cook up a mapping that you get just by taking the product. So phi is going to be a mapping from this into the Cartesian product of the W's. And that's defined by well, let's see. Let's let the coordinates in this one be x and the coordinates in this one be y. And then take this to be simply defined by taking the product, taking the ordered pair corresponding to the two given coordinate representations. So this is going to be the ordered pair C1 x C2y. So that gives us a mapping into this. So this is a mapping. This is, notice this guy is contained in Rn plus K1 plus K2, where n is equal to n1 plus n2. So that gives us a mapping. And notice this indeed provides a local coordinate representation, is a local coordinate representation. Local coordinate representation for the Cartesian product, m1 times m2. Easily check that it satisfies all the conditions. It's clearly a one-to-one map, and it's CQ if these are CQ. These are CQ local coordinate representations. So that means that this Cartesian product is indeed a submanifold, Q-dimensional embedded submanifold, that is. Because you can do this in a neighborhood. Remember, these V1 covers all of M1 and V2. By choosing V1 and V2 appropriately, you can include any point of M1, and by choosing V2 appropriately, you can choose any point of M2. So this gives you a map that's defined in a neighborhood of any given point of M1 Cartesian product M2. So indeed, we've proved that M1 cross M2 is a submanifold, is an n-dimensional, where n is n1 plus n2, submanifold, embedded submanifold, of Rn plus Rn plus K1 plus K2. So that's the thing, and let's work out now how the areas work out. That's what I particularly want to mention. So according to our formula here, the formula for the standard area formula, if we apply the standard area formula to the local coordinate representation Phi1 on V1 and Phi2 on V2, so take any A1, A2, so take AJ contained in MJ intersect WJ, J equals 1, 2. Okay, and then according to the area formula, this one from the Euclidean space, that tells us that the integral of phi to the minus 1, or the integral of phi to the minus 1 AJ times the Jacobian of phi j, that's right, is equal to, now this, remember local coordinate representations are one-to-one, so instead of getting this complicated thing, you simply get the n-dimensional measure of the image. So that's equal to n-dimensional measure of phi j, this is phi j to the minus 1 aj. We get phi j to the minus 1 aj, which of course is just the n-dimensional measure of aj. Like so. So that's good, and so then let's compute. So we know that that's standard formula for the measure for the. In fact, this is, as I mentioned before, this is what the differential geometers would call integral of square root of g equals the volume of the image. That's standard geometric terminology for that. And now let's compute. We have to. I want to see how these work out when you compute the Jacobian of this thing. So we're going to compute the corresponding area of this thing. So let's do that. Okay. So let's try that. So let's do the, so what is J? So we want to compute this quantity for this mapping, capital C. So what is the Jacobian of capital C? That's equal to the square root of the determinant of di capital C dotted with dj capital C, where now j runs from 1 up to, let's see, x is in Rn1 and y is in Rn2. So I and j run from 1 up to n1 plus n2, right? But of course, when you differentiate this second component with respect to x, you get 0. So in fact, this matrix here, dic dotted with djc, det of that matrix is simply determinant of, you can work it out, it's simply determinant of dxi. So you take dxi, the derivative with respect to the xi's of c1 dotted with dxj, c1. That's an m, ij goes from 1 to m, so that's an m by, it's an n1 by n1 matrix. And then you have the zeros in the off-diagonal terms because of what I said. When you differentiate the y, the function depending on y with respect to the x variables, of course, you just get 0. So in these off-diagonal areas, you get zeros, and down here we get the y derivatives. Again, an m by n matrix with d psi 2. So this is d yi c2 y dotted with d yj c2. And again, ij goes from 1 to m. And take the determinant. Well, that's just the product. It's just jc1 squared times jc2 squared. So indeed, you get that jc is indeed, as you would expect, jc is indeed equal to simply the product. This at xy is simply the product of jc1 at x times jc2 at y. So that's, I guess that's no surprise. That's what you would have guessed, right? But indeed, that turns out to be the case. So now when you compute the integral of a1 cross integral, let's see, we want to compute now the n-dimensional, sorry, this is nj, j equals 1, 2. We have both of those. Now we want to compute the n-dimensional Hausdorff measure of A1 cross A2. Well, you see, by this, it's just the integral of C1 to the minus 1 A1 cross C2 to the minus 1 A2 of this product, J1, JC1 X, JC2Y, and then DHN, where N, remember, is N1 plus N2. So that's that. And so that's what the formula tells us in this case. And you see, you can just use Fubini's theorem here. This is just an integration down in R, downstairs in Euclidean space. And Fubini's theorem applies in Euclidean space. So by Fubini, this is exactly just the product of the separate integrals, which we know gives us the product of the HNAJ. So this is HN1A1 times HN2A2. Now, you may think I sort of spent a bit of time on something that's completely obvious there, and why did I even bother? Well, I wanted to point out something. There's a danger here. Notice that this indeed works. You do get the correct formula when you take the product of submanifolds, but if you take simply the Cartesian product of any two subsets of Rn, Hausdorff measure does not behave like that in general. That is, so note, if A1 is just a subset of some Euclidean space, say RQ1, and A2 is another subset, measurable, that's fine. They can even be Borel sets, that doesn't matter. Then in general, it's not true that Q1 bigger than N1, say, and Q2 bigger than N2. In general, it's not true that N1 plus N2, A1 Cartesian product, A2. In general, this is not correct. It's in general not the same as this. Because after all, Fubini's theorem doesn't say anything about things like that. Fubini's theorem is a theorem on product spaces of measures, and this is not necessary. There's no particular product measure that works here, but Hausdorff measure doesn't behave like a product measure in general. But of course, everything's okay if you're talking about Cartesian products of smooth submanifolds. Then I've just shown that everything does indeed work out. But I did want to point that out, that there's a danger there. It's not necessarily true that you get the product when you take Cartesian product of two sets and take the Hausdorff measure. Okay, so that's good. Let's see, what else did I want to mention here? Yeah, we also want to be able to compute on the submanifold M now, so let's talk about that a little bit. So let's go back to the setting where we've got our submanifold M. So M is embedded, n-dimensional embedded submanifold. And let's talk about gradient and divergence. On M, on such a submanifold M. Yeah, good, we've still got the star here. I want to refer to that. So suppose that we've got a Lipschitz map. Let's take a Lipschitz map from M into R to begin with. And I wanted to find the gradient on M of f at x. So I want to be able to use directional derivatives freely and to use their linearity properties as well. So in particular, that's important for what we're going to be doing here. So I want to be working in one of the Hn almost every points where this is true. So assume star holds. So x in M such that star holds. Then we can talk about the gradient of M. So the definition is gradient M of f at the point x is simply defined to be that you take the directional derivative of with respect to an orthonormal basis. So you take an orthonormal basis tau 1 up to tau n, that's his orthonormal basis for the tangent space of M, and you take the directional derivative of f in the direction tori, and notice that's a scalar function because f is real valued, so that's a scalar, and you multiply that by tori. Now notice that's a linear combination of vectors in the tangent space, so this is certainly in the tangent space. So it's by definition certainly tangent, and while we're at it, let's keep in mind that our submanifold here is sitting in the Euclidean space, some high-dimensional Euclidean space, Rn plus k. See, this is sitting in Rn plus k. So these tangent vectors are all in Rn plus k. So that means that this gradient has got n plus k components. Grad, which we could call grad 1 m fx up to grad n plus k m fx. And grad j just means the jth component of this vector in Rn plus k. So grad j fx is simply the jth basis vector in Rn plus k dotted with that vector, grad m fx. Okay, so that's that. And now let's see if we can get a more explicit expression for grad j. So grad j is the jth component of this. So grad j m fx is equal to just the dot product of this vector with ej. Now this is a scalar, so we're just dotting with that vector. So this is sum from I equals 1 up to n d tor I fx, and then you take dot ej with the ith basis, with this ith basis vector, but that's just the jth component of tor I, so tor ij, right? And yeah, so that's that. And notice that this, remember these guys are linear. We're at a point where one of these, we're working at one of these almost every point, everywhere points where you've got linearity in the directional derivatives. So I can put this scalar in here. So this is the sum I equals 1 up to n of d. Oh, I can put the sum down here. So this is the directional derivative in the direction of the sum I equals 1 up to n tor ij times, that's a scalar, times tor I, that's a vector, applied to f evaluated at x. So I can write it that way. And now we recognize this. That's exactly the tor ij times tor I summed from I equals 1 up to n is exactly the orthogonal projection. I can rewrite it. Yeah, in fact, let's do that. I can rewrite this as the sum I equals 1 to n of ej dotted with tor I times tor I. But that, you recognize that. That's exactly the formula for the orthogonal projection of the vector ej onto the tangent space, right? Whenever you have a orthonormal basis, you can write down explicitly the matrix of the orthogonal projection. It's this guy. So this is exactly the orthogonal projection onto the tangent space of M at the point X of Ej. So this is the orthogonal projection. That's the orthogonal projection of Rn plus k onto the tangent space, Txm. Exactly what it is. So see that we could call that, a nice notation for that might be EJT, meaning the tangential part relative to the tangent space. Orthogonal projection into the tangent space. It's the tangential component with respect to this space. So that would be this. What's that? Tau. Yeah, well, these are, remember, tor 1 up to tor n are orthonormal basis, right, for the tangent space. Here it is here. Orthonormal basis. And then to get the orthogonal projection, you just, into the span of those, which is Txm, you just take the vector you want to project and dot it with that and multiply by tor I and sum, right? Okay, so that's Ej tor. So another way to write this jth component is it's the directional derivative of the tangential part of the ith standard basis vector. hitting F at the point X. That's a nice way to look at it. Very good. And there's one other point about this too that's useful. If F, let's see, we're getting a bit short of space here, so let's go over here. If F is actually C1 rather than just Lipschitz, if it's actually C1 in a whole neighborhood of M, in an open neighborhood of M, so then the schematic one-dimensional picture would be M's here, and then you're talking about F being defined in a whole neighborhood of M. Let's call it U. So this would be U. So you have the F is actually C1 in a whole neighborhood of M. And then you can give an alternative description of this, which is often more convenient. Namely, this guy is grad MF. Here it is here, this thing. And if F is actually C1 in a neighborhood, you can rewrite this to directional derivative in the more standard way of this would be a directional derivative in Rn plus k in that case, rather than just a directional derivative in the manifold. So this would actually be tor I dotted with the gradient taken in Rn plus k of F at the point X. This is provided F is C1 in U, in a neighborhood U. So U is open containing M. So as long as that's true, you can rewrite this as just the dot product of the full gradient of F dotted with tor I. And you see, again, it's exactly like this thing. Again, that's just the orthogonal projection onto the tangent space of the full gradient in Rn plus k. So this is equals the orthogonal projection onto the tangent space of the full gradient taken in Rn plus k of F at X, which is very useful, but remember that only works if you know that F is already defined in C1 in a whole neighborhood. So you can't use that in general if you've just got a Lipschitz function. And I'm not being picky about differentiating between Lipschitz functions and C1 functions in a whole neighborhood. For us, that'll be of crucial importance when we start talking about rectifiable sets and things like that. So it really is an important distinction that you are able to handle just Lipschitz functions on the manifold. So, okay, so then you get this formula that grad MF at X is the orthogonal projection into the tangent space of the full gradient Rn plus k of F at X. Right. Now, there's one other important object, and that is if you take, let's do it here, in fact. So if X is a vector function with components xn, it's a vector function on M with values in Rn plus k. So each xj is Lipschitz, real valued Lipschitz on M for every j equals 1 up to n plus k. So take a vector function like that. Then you can talk about the tangential divergence. It's denoted div sub m of x of this vector field capital X at the point X. We're still talking about one of these points where you can take all the directional derivatives and they're all linear. then div mx at x is simply defined to be the sum I equals 1 up to n plus k of grad m tangential gradient ith component of xi. Sort of looks like the ordinary divergence of a vector field in Rn plus k, except that we're using the tangential operator here to compute these. And let's give an alternative description of this, because we know what grad mi looks like. It's ej dotted with ei dotted with grad m, so this can be written as the sum I equals 1 up to n of ei dotted with the gradient of the ith component, gradient of xi at x. Now the gradient at xi we have by this formula here. It's this. So this can be written as sum I equals n 1 to n plus k rather, not n. Sum I equals 1 up to n plus k. ei dotted with, now this is the sum j equals 1 up to n of directional derivative of xi in the direction toward j times toward j. This is at x times the vector. Notice this is a scalar times toward j, which is a vector. And that's tor ij, so we can play around with this using linearity again. So this is tor j. Notice that's exactly the same as the sum from j equals 1 up to n of tor j dotted with d tor j of the vector function x. Because this ei times xi just gives you the vector function x. So this is d tor j x hold on. Did I say that right? This is ei. No, that's correct. And this is tor j. So let's check that that's right. I rewrite x as sum xi. Sum ei times xi, and then this is tor j dotted with ei times xi, and we're taking d tor j xi. Yes, that's correct. So that's an alternative way to write this. So we have two formulae for the tangential divergence. You can write either div mx in the original way, that's the sum from I equals 1 up to n plus k, grad mi xi at x, or you can write it in terms of the orthonormal basis as the sum j equals 1 up to n tor j dotted with d tor j of the vector function x at the point x. Yep, so that's that. And there's a similar remark if you know that xj's are C1 in a neighborhood like this. If x1 up to xn are actually C1 in a neighborhood U, an open set U containing M, then you can use this kind of formalism here and you can check. And div mx is the sum. Now, let's use the second identity for this. So that's the sum j equals 1 up to n tor j dotted with d tor j x, vector function x, evaluated at the point x. And this d tor j x can be written just as, so this is the sum let's see, let's write x as we did before as the sum x ej times xj. You can always rewrite the thing in terms of its components. I better use a different symbol there. This is ei times xi. It's better. Then this is tor j I. When you dot tor j with ei, you get tor j I. And then you get d tor j xi at x. Yep. And that's still summing, so we're summing from j equals 1 up to n, and summing I equals 1 up to n plus k. Okay, and that's, and again, if the x 1 up to x in a C1 in U, we can rewrite this as a dot product. So this is exactly tor jk times the jth partial. That's what the directional derivative is when you're working in Euclidean space. So you can rewrite that in terms of just the ordinary partial derivatives, as long as you remember to multiply by tor jk. That's the kth component of tor j. Now again, this guy here, see that guy there? That's exactly the I-kth component of the orthogonal projection matrix. So it's PTXM is exactly given by, has a matrix exactly tor sum from j equals 1 up to n, tor, let's call it q, equals 1 up to m, tor qi, tor qj. And that's an n plus, so ij, it's an n plus k times n plus k matrix. N plus k matrix. So in other words, this says exactly that that div mx, as long as x is C1 in a neighborhood of M, you can rewrite div mx in a nicer way. Namely, it's just just use the, let's call this matrix Pij. So it's the matrix Pij. It's the matrix of this orthogonal projection. Let's call that Pij, or maybe better to call it Pmij, to emphasize that it's the orthogonal projection onto the tangent space of M. So this is the sum Ij equals 1 up to n plus k of Pmij dixj. That's a third expression. This one is valid provided x is C1 in a neighborhood of U. In fact, let me give an example of this. Let's compute an example. So we've got this submanifold M sitting in the Euclidean space, and maybe the origin's down here. This is the origin of the Euclidean space. This is Rn plus k. Let's just take x to be the radial vector field that you get from taking the point x. So let x at x be equal to x, just the radial vector field. Remember, we're in Rn plus k, so this is just so these are just the coordinate functions, x1 up to xn plus k. Now let's compute. According to at a point, so we go to a point x of M. Notice this is one of the cases where x is C1. In fact, these are obviously C infinity functions in all of Rn plus k. So certainly this particular formula can be applied in this case. So let's compute. So what's dixj at x in this case? Well, dixj at x, it's just di of little xj. It's the partial derivative of the jth coordinate with respect to the ith coordinate. That's just the Kronecker delta ij, right? So this is Kronecker delta ij. It's equal to 1 when I is equal to j, and it's equal to 0 when I is not equal to j. So in this case, we get that div m of x, that's the radial vector field, is equal to the sum Now here it is here. ij equals 1 up to n plus k times the orthogonal projection matrix, Pijm, times Kronecker delta ij. And of course that's just, you just take I equals j and it just becomes a sum over one index. So this is just the sum. In other words, it's just the trace. It's the sum from I equals 1 up to n plus k of Pii m. And now let's think about that. P is an orthogonal projection onto an n-dimensional subspace of Rn plus k. So what's the trace? If it were a one-dimensional subspace, the trace would obviously be 1, right? So the trace is n, right? The dimension of the space. So this is identically equal to n. It's constant. Equals the dimension of m. So that's, we're going to make use of, actually this turns out to be we're going to need this computation a bit later, so we should keep this one in mind. But when you plug in the radial vector field, you just get the trace of the orthogonal projection, which is n. Okay, let's take a 10-minute break then. Yes.
Is it a good context info that
How's the definition of product space?
probably like unrectifiable set?
Yeah, that's right. When the A's are when the A's are nasty sets, not rectifiable. In fact, there are even an example in Federer where you've got two sets of measure 0 and the Cartesian product doesn't have measure 0.
No. It actually is the number n1 p times q.
What's that?
If A1 is just points, A1
Yes.
and A2 are points.
Well, yeah, then that's fine, but that's just an example. That works,
So
right?
your counterexample.
I'm saying there is a counterexample in Federer somewhere. It's complicated because it has to be some sort of nasty set to give a counterexample. But there is a counterexample. So it's one of those traps that people can fall into because you think of Hausdorff measures as behaving like product measures, right? But they do on submanifolds, but they don't in general. So, yeah.
Thank you for pointing out that.
Yeah.
Otherwise,
Yeah. Well, I had to have it.
careless.
I had to have it pointed out to me at one point a few years ago. That I was thinking that if you take two sets of measure 0, then the Cartesian product also has measure 0 in the appropriate Hausdorff dimension. That's not true in general. There's a counterexample in Federer to that. So, of course, it wasn't serious because in the context I was working, there was no problem. But it certainly, I realized I'd been a bit silly not realizing that.
It's quite weird. I mean, the first time I saw this the so-called unrectifiable set.
Yeah.
What is that?
Yeah.
I mean, is that
The only apply to me. Usually I am very careless.
Right.
Immediately conclude.
Right, that's right. Yeah, well, it's good to be a bit frightened from time to time. Yeah.
So by the way, did you send to Ulrich an email?
I would love to take credit for that, but I can't. I can't. I didn't get around to it.
I thought it's
He
because of
already
you.
know that.
If I had been a real hustler, I would have said, "Oh yes, I emailed Ulrich. I'm glad he responded," but actually I didn't. You know.
Well, maybe your mind already made it. You thought about that and that
Right. Well.
already-
Well. I was told by one of my former students that if you work in the public service in Australia, and presumably in other countries too, you would definitely take credit for this.
Would you like to erase the
Let's see. Now, what do we need? Yeah, I think we can erase everything, actually. I think we're going to start off... right, yeah. Maybe leave one thing... maybe just leave that board over there on the right. Yeah, thanks. Yeah, I would have liked to have taken credit for that, but it didn't work out.
Which credit?
Ulrich Nenner is coming, and Junchi thought that I'd emailed him to twist his arm, and it turned out that he thought that's the reason he accepted today to come to the conference.
Okay.
And so, but it turned out it wasn't me. It was he'd already emailed him, but he hadn't replied. You see. So I said, well, I could email him to try and put it. Yeah, that's right. I think you were there when we were talking about it. Yeah, but it turned out I didn't do it.
Okay, wow. The result is good. It's important.
That's right. I would like to take the credit, but no.
Yeah. So I already purchased the difficult thing to the Huawei is about ticket, but I think I try to look at the because holiday start from Monday. The Saturday is some people still need to work, so that's why I decided we go there on Saturday. Easy to get tickets.
Easy to get tickets.
So I was able to get tickets already from.
Good. Great.
Yeah.
Just tell me how much I owe you. No problem.
Yeah, I'll tell you in the end.
Right.
And so I will. So we are going to stay. The first day we will stay in near is something called a Taiwan Gorge.
Okay.
And then we can take maybe a hike.
Okay.
Maybe I think the first day I will take you some other places, and then maybe we stay one night, and the following morning we can take a hike.
Okay.
So there are several hikes.
Okay. Great.
So there's one.
Right. I'm getting a bit worried now. Are you?
No, we take the easy one.
Okay, good.
So
I remember Chun gave me quite a bit of a workout.
Okay, no.
I thought you might be worse.
This one is a little longer, but it's not going up.
Okay,
See,
great.
it's like,
Okay. Yeah.
Maybe I don't know if they have English one. So my friend, they hike there a lot, so they have some. You see the height is 4.1 kilometer. I don't know it's run through or.
That's not too bad.
But you see, it's basically it's flat.
Yeah.
The height is only 60 kilometers. So it's sort of high along the river.
Sure.
See?
Great. Yeah. Right.
And so here is the round trip is like 4 to 6 hours. But I don't think that you need. But
That's
anyway.
probably for someone that's basically crippled, right?
So this is the height that my friend suggests should be good. I mean, there are several heights, but I think this is probably a good height. Hiking because this is national park, so it's sort of like lots of gorge.
Oh, that's
See,
good.
we can
That's good.
hike around the river and then.
Yeah.
So.
Okay. Great.
And
Looking
then
forward
maybe
to
the
it.
next day I will take you to more like the coastal area, and so that's one thing because
So we're on the eastern side of the country, right?
Yeah. So we are going to. I can show you the. Yeah, so we are going. So I show you this is a Google map. So this is Taiwan, right? And so we are going to this something called this is a national park, Taiwan Gorge.
Okay.
And we're going to stay at a B&B.
Yeah. Okay. Great.
So
That's a little bit high up, is it?
No,
Or
it's not that high.
Not that high.
So this is the whole mountain area, but we are still stay. Yeah, I mean, like we'll stay around here. We're not going up. There's hiking to the mountain, but we're not going to the mountain.
What sort of heights of other of the peaks in that area? And what sort of heights do they get to actually?
It's basically it's all in the mountain area.
Yeah. But I mean, for a start, what's the highest peak altogether in Taiwan?
You mean the peak
The highest peak, yeah.
is the J Mountain.
Yeah, and how high is that?
It's like 30, almost 4,000.
Yeah, oh, that's pretty high.
Yeah,
Right.
it's somewhere in the middle here, so it's I can show you.
It's not to be sneezed at.
Yeah. So I guess the peak is here, something called the J Mountain here. This is so this is what. This is pretty high. So this is 3952, almost 4,000.
Okay, okay.
So this is the peak of the,
Right,
the highest peak.
And it's possible to climb that if you're really serious about it? People do climb it, do
Yeah,
they?
no, because this is like a popular hike now.
Okay.
They have some
So there is a trail up there.
Usually the way to go there, there's some kind of like a hostel.
Oh, okay.
Like in maybe like Virginia know about, so it's like maybe like 1,000 meters lower than it. You see?
Okay.
So usually people go there first,
Right.
And then you
Sort
stay
of-
there overnight.
Right,
And then,
so they have to make a reservation,
and then
presumably,
the
right?
next morning you hike up here.
Right.
But the problem is that usually it's good to reserve that place say by yourself.
Yeah.
But maybe you see there are some travel agents. They already book
Right.
the place.
Okay.
It's easier to go with a group.
Yeah, okay.
I think that's what Gingy was
Right.
talking to you.
Yeah. Yeah,
So we have no class meeting on Saturday, though, right?
that's right. Yeah.
I think we should announce
Oh,
it.
yeah. Oh, they don't know that? Yeah.
I think they're not sure about
Okay. Right. I wanted to mention that there's no meeting of this class on Saturday, right? There's no make-up meeting on Saturday.
Already mentioned that.
Okay, good. Right. And this week's week 4. They're on the web page, but let me tell you anyway right now. They're problems 2.7, 2.10, and 3.5. Okay. Okay, so let's see. We need to talk about first variation. So the first variation of M, well, before we do that, though, I need to talk about the second fundamental form. So that's the next topic, which I seem to have got lost somewhere here. Okay. Well, guess that got lost back in my office, but that's okay. So, so we need to talk about the second fundamental form of, so we're in the same setting now. M is a submanifold of n-dimensional in some Euclidean space, Rn plus k. And now we suppose that M is at least C2. So most of, in fact, everything we've said so far was valid if you merely have a C1 submanifold. But now we need to take a C2 submanifold. So that means that all the local coordinate representations have to be at least C2 in order for it to be called a C2 submanifold. And then go to a point X in M, and then the claim is that near X, so the claim is that near X, in some small neighborhood of X at least, there is an orthonormal basis, is a C1 orthonormal, there are C1 vectors. TOR1 depending on, let's call this point that we start at x0. And then near that point, you claim that there are orthonormal C1 vectors and TOR1x up to TORn plus kx. C1 vector functions, TOR1 up to TOR1, such that the first n of these always provide a basis for the tangent space. And the remaining n, this is, so I should have said C1 orthonormal vectors. Orthonormal vectors, so that means TOR I dotted with TOR J is Kronecker delta ij. For every I not equal to j, for every ij equals 1 up to n plus k. And the claim is that you can find such an orthonormal basis such that the first n, TOR1x up to TORnx, are a basis for are in TXM. So they're an orthonormal basis for the tangent space, right? The first n of them. And that means that the remaining k of these must be an orthonormal basis for the normal space, right? Normal to n. So and TOR n plus 1x up to TOR n plus kx are in TX perp. The orthogonal complement. It means orthogonal complement. In other words, the vector's orthogonal. They're orthogonal to the tangent space. So now it's not quite, now that's one point is if you're not too familiar with differential geometry as yet, then you should be aware that you can't do this globally in general. Even on the unit circle, it is not possible to find on the unit circle, right. Actually it is. On the unit sphere, I guess, right? The unit sphere, it is not possible to find such things that are defined globally in C1 globally. You have to have a discontinuity somewhere when you try to make such a construction. So you better put a waist around this, I guess. So, but you can do it locally, no problem, because, for example, one way to do it is to take a local coordinate representation, that's C1 in a neighborhood of any given point, and that gives you initially, and they're not orthonormal, the partial derivatives of that local coordinate representation span the tangent space, but they're not orthonormal. And then you can just add on k extra vectors to give you an orthonormal basis for all of Rn plus k, and then you can simply apply the Gram-Schmidt orthogonalization process. Now the Gram-Schmidt orthogonalization process has the additional property that people don't always realize, that if you start off with n plus k linearly independent vectors, and the first n of them span some subspace, in this case they're spanning Txm, then you apply the Gram-Schmidt process. The Gram-Schmidt process is inductive, so that the first n of the new orthogonal vectors you get from that process are in the same subspaces spanned by the first n that you had originally. So it'll preserve the fact that the first n of them are still in the tangent space in this case. So the Gram-Schmidt process gives you such an orthonormal basis, and it's C1 in a neighborhood of the original point, x0. So no problem about that. And so let's use the slightly different notation for these guys. Let's call these guys nu1, nu1 up to nu k, or k of these. So these are an orthonormal basis for Txm perp. Okay, so let's agree that we've got we've done this process and we've got at least a locally defined orthonormal basis of this type. And these are an orthonormal basis for the tangent space. Okay, then you can define the so-called second fundamental form. of n. Definition. The second fundamental form is define B at a point x0 of tor eta, where tor and eta are tangent vectors. In fact, let's do this generally at a point x. Tangent vectors. This is defined to be minus, it looks a bit weird at first, and I'll explain. If you haven't seen this before, at least it'll look a bit weird. It's the sum from j equals 1 up to k. We're going to be using these orthonormal basis for the normal space here. So it's directional derivative of nu j dotted with eta. This is at the point x. Directional derivative at the point x dotted with eta and then multiplied by nu j at x. And you do that for each pair, tor, eta, and txm. So that's the definition of the second fundamental form. It's called the second fundamental form of M. And notice we do need, definitely need M to be C2 to do this, because as I said, you get these by applying an orthogonalization process to the partial derivatives of a local coordinate representation. So that means if you want to differentiate these, you're going to be taking two partial derivatives of the local coordinate representation. So you definitely need the local coordinate representations to be C2 in order to do this. Okay, so that's the definition. Now let me explain the geometric significance of this. So the geometric significance the following works out, namely take any curve, so take any curve gamma defined on some interval minus epsilon into Rn plus k, and this should be C2 curve, and we want the usual conditions to hold, namely gamma at 0 should be equal to the point x that we're interested in, and gamma, and then let's agree that we make gamma prime 0 be equal to gamma prime 0 will be a tangent vector, remember, that's definition of tangent space, but let's call it tor. And now let's talk about bx tor with that tor. Okay, that's minus sum j equals 1 up to k d tor nu j at x dotted with tor. So we're taking, notice we're taking tor. We're taking one of the diagonal terms here, tor. Dotted with tor times nu j at x. And observe that that's the same as, so that's the definition, but now let's observe something. If I take gamma prime t dotted with nu j, what I want, yes, nu j at gamma of t, notice that's identically 0, because gamma prime t is always in the tangent space at gamma t, and nu j is in the normal space at gamma of t. So that's an identity. That's identically 0 for mod t less than or equal to epsilon. But so we can differentiate this with respect to t, and this gives us gamma double primed t dotted with mu j gamma t plus, now what happens when you differentiate this one? Well, that's our definition of the directional derivative with respect to the, that's exactly how we define directional derivative. So that's the directional derivative in the direction of mu prime of mu j. So plus, and we've still got this gamma prime guy here, so this is gamma prime t dotted with the directional derivative in the direction gamma prime t of mu j evaluated at gamma t. Like that. That's exactly our definition of, that's how the way we define directional derivative. And now let's take t equal to 0. Then you get gamma double prime 0 dotted with mu j at, and gamma at 0 is equal to x. Where did I say that? Here. Gamma at 0 is equal to x. So plus, and gamma primed is equal to tau. So plus tau dotted with, and then this is d tau, directional derivative in the direction tau, mu j, at x. Like that. And so in other words, gamma double prime 0 dotted with mu j x is equal to minus this. Now, while we're at it, I'm going to take this onto the other side. So this is equal to 0. So 0 equals this. Equals 0. So, so I'm going to take this term onto the other side, put a minus sign in front of it, and while I'm at it, let's multiply by nu j and sum on j. So this implies that the sum j equals 1 up to k of this times nu j is equal to, or minus, there's a minus sign because I put this term on the other side, is equal to the other term. That's gamma double primed 0 dotted with nu j at x times nu j at x, summed from j equals 1 up to k. And see this is exactly, remember nu 1 up to nu k is an orthonormal basis for the normal space at x. So this sum here is exactly the expression for the orthogonal projection of this vector onto the normal space. So this is exactly the orthogonal projection of the second derivative onto the normal space. Equals that. So in other words, we get this nice formula that sort of tells us what second fundamental form really means. Namely, if you take any such curve and you take the normal component of it as it passes through x, then that's exactly equal. Notice this guy is exactly, this guy is exactly the second fundamental, oh, where are we? What did I do? Sorry, yeah, this is minus gamma prime, sorry. Let's see. Oh, right, okay, I had this guy, right? Gamma double, right, so I get that, and this is the other term, right? This is d, so right, so the other term is this one, right? So this is wrong. This is supposed to be, yeah, I put the second derivative term onto the right. There it is over there, and then I keep the first derivative here. So that's the one with the directional derivative in it. So that's gamma prime 0, which is tau. So I get a tau. From this term, I get a tau.
This is just second fundamental form?
Yeah, exactly. That's what it is. Yeah. Thank you very much. Right. That's what I was trying to say in my own clumsy fashion. Right. Tau dotted with d tau nu j times nu j at x. These are all evaluated at x. Is equal to that. So in other words, we get this, that this is exactly the second fundamental form at the point x of tau. So that's the geometric. This is called the normal curvature. If mod tau equals 1, So let's agree that we take mod tor equals 1, otherwise there's a scaling factor involved. So let's agree that we take a unit vector. Otherwise it's completely arbitrary. And this is called the normal curvature of M in the direction of tor. At the point X. It's quite a mouthful. Normal curvature of M in the direction. So that's what the second fundamental form does, at least as far as these diagonal terms are concerned. It measures the normal curvature. It measures how the manifold is curving normally. Notice that it's very important that this is normal component. If it were general component, it would be totally meaningless, because you see, here's the picture. We're measuring how the manifold's curving as it sits in the Euclidean space. Here's the point X. See, we might have picked a curve that does this. It's a really high curvature in this tangential direction. Well, but that doesn't play any role in this. We're only taking the normal component of the curvature. By the way, notice that this normal curvature, because it's equal to this, is totally independent of which curve gamma you pick. Totally independent of which curve gamma. And the reason that works is because we're looking at the normal curvature, not the curvature in the manifold. We're not interested in that. We're interested in how the manifold's curving. So that's an important identity that really tells you what the second fundamental form means, at least as far as these diagonal terms. Now let's talk about what the general off-diagonal terms, what the mixed terms mean. There's a similar interpretation for those. So let me do that. So let's talk about the, let's leave that. Let's work up here. So let's talk about the general terms now. Beta, here it is here. This is our general definition. So can we give a geometric interpretation of this guy now for arbitrary tor eta? Well, you can do a similar thing. Similarly, let phi, instead of taking a curve, you take a mapping from R2. So let phi be a mapping from minus epsilon epsilon cross minus epsilon epsilon into Rn plus k. So we've got two variables. Let's call them u and v. So phi is mapping this little epsilon minus epsilon. It's taking this little square and we're mapping into the manifold. So we require that phi of minus epsilon epsilon is contained in M. Similar conditions to the curve case. And we want phi at 0, 0 to be equal to the given point x. And we want the partial derivative of phi with respect to u to be equal to the given vector tor. And we want the partial with respect to v to be at 0, 0 to be equal to the given vector eta, because we want to work out this second fundamental form at tor eta. And again, take these to be of length 1 so that we don't have to worry about scaling factors. And then by a similar argument to the one that I gave here for the curve case, you can check that when you take the mixed partial derivative of this function phi, du dv at 0, 0, and you take the normal part of that at the point x, that is indeed equal to the second fundamental form, tor eta. So that's the meaning of the second fundamental form. It measures how the thing is curved. at least as far as the normal curvature is concerned. And it even gets the mixed partial derivatives to work out. And yeah, there was something else I wanted to say about that. Yes. Notice this also shows that this is symmetric. That wasn't clear from the definition. This is symmetric in torr and eta. Because this guy is symmetric, mixed partial derivatives, symmetric. So that's the meaning of the second fundamental form. And an important particular quantity related to this is to take the trace of this. When you put torr and eta equal to torr I, where torr 1 up to torr n is an orthonormal basis for the tangent space, you take the trace. So definition, sum I equals 1 up to n Vx torr I is called the mean curvature vector. Mean curvature vector of m at x. And so it's the trace of the second fundamental form. And here of course, torr 1 up to torr n is an orthonormal basis for the tangent space. Now notice that we can interpret that geometrically too. Go back to our formula for the, see it's this. It means that you take n mutually orthogonal curves passing through the point x0, and then you take the average of the normal curvatures of those. You take the sum of the normal curvatures of those. So this is equal to the sum I equals 1 up to n gamma I double prime at 0 perp. So it's the sum of normal curvatures where gamma j t is a curve contained in M with gamma j 0 equals 0 and gamma j primed 0 equals torr j. So so that it really does measure the sum of the normal curvatures at the point. You take n mutually orthogonal curves passing through the point, and you take the normal curvatures of them, take the sum, that gives you the mean curvature vector. Okay, so that's good. That's an important quantity for us, and we'll come back to that as we go along. Now, we need to talk about first variation. Okay. And so usual setup, we've got a C, for the moment C1 submanifold at least, and we're going to require it to be C2 and a little bit later, but for the moment just C1 submanifold, n-dimensional, and in the usual Euclidean space Rn plus k. C1 submanifold. And I'm going to think about perturbing M. Now it's really hard to draw this if you try to draw it in high dimensions, so I'm going to do a really schematic picture of what's happening here. I'm going to just think of M as being a one-dimensional curve like this, and Rn plus k is here. So this is sitting in Rn plus k. And I'm going to think about perturbing M using a one-parameter family of maps. So we take a one-parameter family. So let C be a map from defined in a neighborhood of U. So let's take an. In fact, let's take this from minus epsilon epsilon. There's going to be two variables here. Cross M into Rn plus k. Rn plus k is the ambient space here. And let's write phi equals phi t of x, where the t is in the interval minus epsilon epsilon, and x is in m. And let's impose some restrictions. Let's agree that phi at time 0 starts off as the identity. This is for every x in M. That's the first restriction. Second restriction is that phi outside a given compact set, so there's going to be some compact set here, K. Outside a compact set K, phi fixes everything at every time. So this is equal to x for every x in M minus K and for every t in minus epsilon epsilon. And the other thing is that this, of course, should be at least C1 because I'm going to be differentiating. So this should be a C1 map. Okay, that's good. And so let's agree that phi sub t at x should be just the map at t and x. So you can think of phi sub t as being a one-parameter family of maps hitting the x variable. So phi sub t is a map from M into Rn plus k. And that's what these things are. This is M, and these perturbations are what you get when you take phi t of M at different times, like that. So you get this variation. Now, let's look at the variation of the volume. So remember, the volume is just the n-dimensional Hausdorff measure. So let's look at the volume of phi t m intersect k. M intersect k, this compact set. Remember, phi keeps everything fixed outside k. So we're interested in the initial rate of change of that. That's called the first variation, ddt evaluated at t equal to 0. It's called the first variation. You could also take higher derivatives. The second variation would be the second derivative at 0, and so on. But for us, this is the most important variation, the first one. And now we would like to work that out. Well, and at first sight, it looks hopeless. How on earth are you going to work? How on earth are you going to compute that? But remember, we've got the area formula. So we can compute it very easily. Hn, so this is equal to what? So Hn of phi t, m intersect k, by the area formula is equal to the integral over m intersect k of the Jacobian of phi t, dhn. So that's nice. So we just have to compute the Jacobian, and then we can differentiate this by differentiating under the integral sign. Remember, everything's C1 here, so it's perfectly legitimate to differentiate over the integral sign. So we can do that. So let's compute the Jacobian term. Well, let's think about this. Phi t starts off at x when t is equal to 0, and we've got to make up a name for the first derivative at 0. So let's agree to call that capital X. So capital X is the initial velocity vector. And the initial velocity vector is simply the partial with respect to t, the rate at which it's changing with respect to the t variable, evaluated at t equal to 0. So that's oh yes, sorry. I want, yeah, that's right. I need this to be at least C2 because I want, I need this to be at least C2 because I want to be able to differentiate x as well. That's the second derivative of phi. So we need this to be at least C2. Notice M needn't be C2 though, it doesn't matter. As long as this phi, these phis are just defined in the surrounding space. So no, well actually, well no. The way I set it up, these are defined in M, but these could be C2, they could be the restriction of a C2 function in the surrounding space. So it doesn't mean M has to be C2. In fact, it's important that it needn't be. M could be just C1, it would be perfectly okay. You could simply take a family of C2 functions defined in an open set around M and then we just restrict to M. So that would be perfectly all right. In fact, typically it's what you do. And now we have to compute the Jacobian phi t. Now let's try to do that without getting in a big mess. Notice that if we use a Taylor expansion of phi tx, we get the first term is, of course, just x at t equal to 0, and then we get the t times the first derivative at 0. So that's t times x at the point x. And then there's an error term which is lower order. So we can put t times x plus the error term, and the error term goes down to 0, even in the C1 sense. So it depends on x and t. Ext tends to 0, like so. So we can do that, and then we can compute the Jacobian. So let's use this expansion to compute the Jacobian of phi t. Remember, this is phi sub t. Phi sub t of x. So let's compute the Jacobian. Remember, in order to compute the Jacobian, we've got to take di dtor, we've got to take an orthonormal basis. Orthonormal basis for the tangent space of M. And then we've got to take, if we were in Euclidean space, we'd take the ith partial of phi t dotted with the jth partial of phi t. But here we've got to take the ith directional derivative with respect to tor I, that is. So we've got to take d tor I phi t at x dotted with d tor j phi t at x. And then we've got to take the determinant of that. And finally, we have to take the square root. So j sub phi t of x equals the square root of that. And that's equal to the square root of the determinant. Now, let's work this out. D, here it is. So d tor I phi t at x. Let's see, what's d tor I of x? It's d tor I of the radial vector. Well, think about a curve going through there. That's just tor I. D tor I of x is just tor I. Think about it. Remember, this was defined in terms of taking a curve, gamma, passing through x, and taking the derivative, so that the derivative is equal to tor I. Well, this is the identity map, so it'll just give you the curve back, and when you differentiate that, you get the velocity of the curve, which by definition is tor I. So nothing to check there. It's just tor I, that term. And then this term is plus t times the directional derivative of x in the direction tor I at x. And finally, the error term, which is EI, let's call it. Now, notice this, I swept something under the carpet here. Not only does the absolute value tend to 0, but the derivatives of E tend to 0 too, because phi is C2, and this is the error in a C2 expansion. So this means that d tor I, E, also tends to 0. So this term tends to 0. D tor I, E, tends to 0. So, and it's still got this factor t in front. So we just have to work this out. So this is det tor I plus t times d tor I of x plus small o of t. Meaning that that's a quantity that even after you've divided by t still tends to 0. And then we're dotting that with the same thing with the j coordinate. So it's tau j plus d tau j x, and this is at the point x. And again, small o of t. You get that? And now tau I dotted with tau j, that's just the Kronecker delta ij. So this is square root of the determinant of Kronecker delta ij, that's the identity matrix, plus d tau t plus, now there's the cross terms, it's t dotted with tau, so it's t times tau j dotted with d tau I of x at x plus tau I dotted with d tau j of x at x, and then plus small o of t. Small o of t. So that means the derivative, you can just differentiate with respect to t and set t equal to 0. Well, this is small o of t, so that doesn't contribute anything as you differentiate and let t equal to 0. This contributes nothing. So we get the ddt of, so that's what j phi is, but remember we want to differentiate that, so I need to work out the derivative of j phi t at x at t equal to 0. Okay, so let's do that. That's equal to, now you've got to brush up on the linear algebra a bit here. If you have the identity plus t times a matrix A, well, I think you can easily see that the principal term that you get is 1 from determinant of I, and then you get certain linear terms in A. That's the trace of A, actually, is the next term that you get here. So it's t times the trace of A, that's the sum from I equals 1 up to n of aii, assuming that A is equal to aij. And then you get terms of order t squared. So apparently we get 1 plus the trace of this. So it's p dt of the square, and mustn't forget the square root, of 1 plus, now it's the trace of this, which gives us 2 times tau I dotted with d tau I. So it's 2t tau I dotted with d tau I of x, and then plus big O of t squared. And the half power gives you a factor of a half, and the 2 gives you a factor of 2, so they cancel. And you simply get, and then you set t equal to 0 after you've done the derivative. So you get actually the sum, you simply get this guy. Sum I equals 1 up to n tau I dotted with d tau I x, but at the point x. And you remember that's exactly our definition of div sub m. That's the tangential divergence. That's great. So we get the tangential divergence. So when we take the derivatives here, and as I said, there's no problem in going under the integral sign. Everything's C1 here with respect to t. Do that at t equal to 0. Then you simply get the integral over m intersect k of div sub m of x. So you get the divergence integrated with respect to hn. So you get the divergence of the initial velocity vector is what gives you the first variation of the manifold. Okay, that's nice. That's a nice computation. And let's see now. Yeah, okay, I've got a couple of minutes. So let me make a couple of points now. Now I did emphasize that m need not be C2 here. It's phi that has to be C2, but that can be defined in the surrounding space. You don't care. So phi can be as smooth as you like. It's independent of how smooth m is. So, but now for a moment, let's just assume that m is actually C2. then in that case we can impose an additional restriction here. We can cook up this phi in such a way that x is a tangent vector. So suppose m is C2 and x is tangent is a C1 tangent vector field. On M. That means that x at x is actually in the tangent space at each point. Notice we're not assuming anything like that in general. I'm just saying, let's suppose for a minute that we've got a tangent vector field rather than a general vector field on M. Then this should be true for every x in M. Then from ODE theory, which I won't go into, you can see a discussion in the text actually of this if you're interested in this. You can actually, from ODE theory, cook up a one-parameter family, phi t. In this particular case, when you've got a tangent vector field, ODE theory implies that there exists such a parameter, such a family, phi t, with, which leaves M invariant. So phi t of M intersect k equals M intersect k for every t in minus epsilon epsilon. That's ODE theory does that. You can look this up, or there's a brief discussion of it in the text. You can actually cook up it's called it's such a you get such a phi t by using the so-called flow generated by x. Look up, Google flow generated by a vector field, and you'll find a description of this. So you can arrange this, but then you see that if you plug that in over here, that means that this side would be 0. Oh, by the way, I didn't emphasize, but it's really important, that notice that we're requiring everything remain fixed outside K. So that means this vector field vanishes identically outside K. So this is not, this identity that we derived at the top of the board there is not valid unless you impose the restriction that X must vanish identically outside a compact K. So this is, where is it? Where's our formula? Where did I write down the first variation formula? Where is it? Oh, here. Yeah. This is OK for every X. For every X which with in C1, for every C1X with X identically 0 outside on M minus K for some compact K. That's very important. It's just simply false, of course, if you don't impose such a restriction. So as long as you pick a vector field that's C1 and identically 0 outside some compact K, then this formula is correct. You get the first variation is given by this. Same thing applies here. X identically 0, we impose that restriction again here. X identically 0 on M minus K. Okay, then the ODE theory guarantees this, it turns out. You can look this up. And that means that this side in our computation would be 0. That would be 0. And that means that, that the divergence, the integral over M of div sub mx equals 0. Integral with respect to Hausdorff n-dimensional measure equals 0. As long as you've got a tangent vector field. That's this condition. And div m, now that's the so-called divergence theorem on a manifold, right? That's, by the way, contrary to popular belief, this does not require that M be orientable. There's no assumption about orientability here, so it's different than Stokes' theorem. Some books, rather strangely, derive the divergence theorem as a special case of Stokes' theorem. Of course, this is a bad idea. because Stokes' theorem only works on orientable manifolds, on oriented manifolds, whereas the divergence theorem works generally, regardless. So, so this is the divergence theorem. For a submanifold. Of course, if you have a manifold with boundary, you can give a version of this for a manifold with boundary, and it looks like the normal divergence theorem where you have a boundary term as well, but that follows easily from this anyway, so we're not losing very much there. But once again, let me emphasize that we are definitely using this x identically vanishing outside a compact set. Then you get 0 here for the divergence theorem. Okay, so we'll continue the discussion here from next time, and I want to say some more things about what this looks like in some special cases. Okay.
So the ODE theory only sort of allow the vector field to be Lipsch continuous, right?
Yeah, that would be fine. Nothing we said required really that x be C1, but turns out that's not quite so important. What's important is that you can relax drastically the smoothness restrictions on M so that you can even do all of this without change on a rectifiable set instead of on a smooth manifold. That's sort of the important thing. Yeah. But we'll talk about that later. Sure.